The next forecasting technique is called the associative forecasting techniques. The associative forecasting techniques are based on the development of an equation similar to what we have in the linear trend that summarizes the effect of predictor variables. What are predictor variables? Those variables that can be used, for example, to predict the values of the variable of interest. For example, consider the value of a house. What do you think are the predictor variables for the value of a house? Such things like the location of the property, the size of the property, the number of bedrooms, the number of bathrooms. Those are the things that we can think of that can be help us to predict the value of a property. So these are called the uh, predictor variables. The associative forecasting techniques try to find a relationship between the variable of interest that you want to make a prediction for and the predictor variables. An example of the associated techniques is linear regression. The simplest form of the linear regression is the simple linear regression. The regression techniques are a set of techniques that try to fit a line to your set of data points. Simple linear regression is the simplest form of regression model that involves a linear relationship between only two variables, the dependent variables or the variable on interest that you want to make prediction for, and the independent variable or the factor or the predictor factor that you think that it has influence on the variable of interest. The goal or the object of the simple linear regression is to obtain the equation of the fittest straight line to your data. Mathematically, this means finding an equation that minimizing your average error of estimation or minimizes the sum of squared vertical deviation from the line. This is called the least square criterion or the least squares method. Suppose you have your data set. The predicted variable is plotted on the y-axis and the independent or predictor variable is plotted on the x-axis. And then you have, for example, a scatter chart built on. The data points that you have, you want to fit a line, a straight line as a regression line to the data. What you can do actually is it's almost infinite ways that you can fit a line, a straight line into your data set. But what you're looking for is the best line. You're looking for a line that has the least estimation error for your forecast. That's what you're looking for. So how to find that line? There is a method called the least squares method, which is basically it's a mathematics optimization, basic optimization method. So what it tries to do is to try to minimize the estimation or the prediction error that your formula, the regression line formula or equation would make um, based on the data that you have. So using this method, you can figure out the components of different components of a square equation for the regression line, which is basically just an intercept and a slope. This is, if you do that using the least square method, minimizing the error, estimation error for your forecast, you're going to get this formula. Y is equal to A, the intercept, plus B, the slope, multiplied by X, the independent variable. So in this equation, Y is the predicted or the dependent variable, the variable you want to make prediction for. X, on the other hand, is the predictor variable or the independent variable. The value of Y is dependent on the value of X based on this equation. B is the slope, as we saw already in the linear trend formula, and A is the intercept. That means that the value of the dependent variable y when x, the independent variable value, is equal to 0. If you look more closely to this formula, it's very similar to what we had for the linear trend formula, except that here the independent variable is x, and in linear trend the dependent variable is time, t. Also, the slope, the equation for a slope and the equation for the intercept are quite similar to that what we had for the linear trend, except that here we have again x, and in the linear trend we had t, the time. Suppose we have built our linear regression model. But how would we know whether our model is good or bad? How can we judge the quality of our model? This is what we want to talk about now. The correlation coefficient, which is shown by a small r letter. R, the correlation coefficient, is a measure of a strength and direction of relationship between two variables. R ranges from -1 to 1, so it only takes values between -1 and 1. It doesn't take any value outside of this. So R is a value between -1 and +1. You can see the formula for computing the correlation coefficient here. As you see, the correlation coefficient equation formula is pretty complex, but don't worry about it. You don't have to literally use this formula because Excel and other software can actually do it for you. So let's talk about the values of the correlation of coefficient R. If the relationship between two variables is strong, the value for R is going to be a value close to 1 or -1. The direction, actually the sign of the value, negative or positive, reflects the direction of the relationship between two variables. So for example, if you have two variables, one dependent and one independent, and the correlation coefficient for those are negative, that means that these two have opposite direction relationship. It means if you, for example, increase the value for one variable, the other variable value would decrease. So they are in opposite direction. On the other hand, if the sign for the correlation coefficient is positive, R is a positive value, that means that the relationship between the two variables is positive in the same direction. It means if you increase, for example, one variable, the other variable would also increase, or if you decrease the value of one variable, the other variable would also decrease. And also, the stronger the relationship between two variables, the absolute value of R would be closer to 1, positive or negative. So R equal to 1, absolute value, that means R equal to -1 or +1, that is the strongest relationship, linear relationship between two variables. Now, let's talk about R square. R square, small r, R square is the square of the correlation coefficient. It's a measure of the percentage of variability in the values of y, the dependent variable, that can be explained by the independent variable changes. So R squared is a measure of qualifying the reflection of your linear regression model. If your linear regression model can describe the strengths or the magnitude of the relationship between y and x, then R square is going to be high value. Actually, R square is just going to be a value between 0 and 1. It cannot be negative, it cannot be less than 0, and of course it cannot be more than 1. So the closer the value of R square to 1, the stronger your regression model is. That means that the changes or the variation in the dependent variable can be described by the independent variable. We're gonna see an example of how to interpret and use these actually criteria in an example. Here is an example of the application of simple linear regression in making a forecast. Healthy Hamburgers has a chain of 12 stores in northern Italy. Sales figures and profits for the stores are given in the table. You want to obtain a regression line for the data that can make a prediction for the profit for the stores, assuming that sales of in terms of 10 millions of dollar unit. So for example, we see in these two columns, the sales and profit. The first column shows the sales values in millions of dollars, and the second column shows the profit. The first thing that you need to figure out is which of these variables is the independent variable and which of these values is the dependent variable, or which actually variable you want to make estimation for. That's very important to be able to develop the right model for your problem. So that's your first step. Figuring out which variable is the dependent variable that we want to make prediction for, that's predicted variable, and also which variable is the factor variable, it's the independent variable or the predictor. So as the problem states here, we are looking to make a forecast for profit based on the amount of sales. So this means that the profit is the dependent variable or y variable, and sales is the independent variable or the predictor that we want to use to make a forecast for profit. So let's go ahead and use Excel to make a simple linear regression model and then apply that to make a forecast for profit based on sales. If the sales of a store is $10 million, we want to make a forecast for its profit.
We have our data in Excel. These are the sales values in millions of dollars, and these are the profit values in millions of dollars. So what we want to do is we want to build a linear regression model, and based on that, using that, we want to make a prediction and forecast for the profit of the company if they have $10 million in sales. So before you do anything else, this is always a good practice to try to plot your data to get a better understanding of data, or whether there's a trend or a deeper understanding. So what I'm going to do, I'm going to actually select our data here. And I'm going to go to the Insert tab right here, the Charts group, and then I'm going to use the Scatter chart here to plot our data. So on the x-axis, we have the sales values in millions of dollars, and on the y-axis, we have the profit in millions of dollars. So it's not a perfect line, but you might be able to see that, yes, it looks like there's a trend. First of all, in our data, there's an uprising trend. That means on average, if you have more sales, you're going to have more profit. And also, you kind of can see you can fit a linear line, a straight line here on this data. All right, so let's go ahead and now do the computation and find, using the formula that we have, find the formula or the equation for this line of the linear regression. So I'm not going to go with the first method that we use. That's like a painful method, because we can actually use the functionality of Excel to do that. So let's go ahead and find the two components, the slope and the intercept for our regression model. And so first, starting with slope, it doesn't matter. You can start with this intercept. Actually, let's do that. So this is intercept, and then it asks for the y value. This is very important, what values you put here. So the y values here is the dependent variable or the predicted variable, what you want to make the forecast for. So here, our predicted variable or the dependent variable or the y variable is profit. This is what we want to make forecast for, right? So I'm gonna grab the profit data first, and then comma, and then the second set of data is the x variables, or here the independent variable, which we have sales here. So I'm going to grab all the data for sales as well here. Then I'm going to close the parentheses here and hit enter, and that's it. So the intercept is 0.0506. Now I can compute, I'm gonna go ahead and compute the slope. The formula for slope is just a slope. Again, the first parameters is y variable or the dependent variable, which is profit here. I'm gonna grab all this data, comma, and then x or sales variable data. I'm gonna select them, comma, and then I'm gonna hit enter, and that's it. So we have the slope and the intercept of the linear regression model, and we can just use this model, not that we have it, to make a prediction for when we have $10 million in sales. That means X is 10. You want to make a forecast for Y. What is Y? What is the profit? Okay. So all these columns and all other data that you see here, this is actually designed to use the first approach, which was the painful approach that you have to do x multiplied by y, x squared, y squared, because you want to use directly this formula to compute a and b. But I actually escaped that because we can actually use the functions that is built into Excel to do that, which is much easier to do and much efficient. So let's go ahead and find the prediction and forecast when x is 10. All right, so before I do that, I'm gonna just put here the equation that we have. So a here is slope is 0.0506, and b here intercept is 0.0506, and the slope is 0.0159. All right, so let's go ahead and make a prediction. So that's equal to y, the profit is equal to, our estimation of profit is equal to a, the intercept, so I'm going to intercept, plus b multiplied by x. So plus b is here, multiplied by x. X is $10 million. Do not put $10 million because all these data that you have here, they are in millions. They do not have the zeros, they are in millions. So, and it says that y, the dependent variable profit, our prediction for profit is 0.21. It's about $200,000 and $210,000 if you have $10 million in sales. All right, so that's our forecast, and now we want to go ahead and actually compute the correlation of coefficient and also the RS squares here. So for the RS squares, we can actually go ahead and find the R first, the correlational coefficient. The correlational coefficient, instead of using this very painful and complicated formula to compute it, you're just gonna use the Correl function in Excel. Correl stands for correlation, and it doesn't matter, it has two sets of data, the first array and secondary. It doesn't matter which one, you put X first or Y first, it doesn't matter. So I'm gonna put sales, and then I'm gonna put profit. You could do the reverse one, and I'm gonna hit enter, and that's it. So R is 0.92, 92%. What does it mean? First of all, this value is positive. That means that the relationship between profit and sales is positive. It means that the more you have in sales, you have the more profit you're gonna make. So that's a positive relationship. And also 0.91 or 92% is a close value to 1. Is close to 1. That means that the relationship between sales and profit is positive. Right, so that's it. Now we're gonna find the R squares. So the R squares is just squares of this value. So that's R square, and that's about 84%. What does this mean? So this means that 84% of changes in profit can be described by changes in sales. That means that your model is capable of estimating the profit, the changes in profit based on sales values 84% of time, or the 84% of changes can be described by the changes in sales. That means that there are other factors that we have not considered. It could be anything, but it's not sales, and that's the remaining 60% that we have here. So 60% of 16% of the changes or variation in profit cannot be described by variation in sales. But 84% actually is it's close to 1 compared that it's not close to 0. And we could kind of understand that based on the correlation of coefficient, because there is a strong relationship between profitability and sales, or the profit and sales.
Next example. The owner of a small hardware store has noted a sales pattern for Windows locks and that seem to parallel the number of break-ins reported each week in the newspaper. So we have gathered this data here, the number of sales and the number of break-ins. So the first thing that we want to do is we want to plot the data and obtain a regression equation, the linear regression equation line for the data, to verify whether there is a pattern, there is actually a linear relationship between the two. And after that, you want to estimate the average sales when the number of break-ins is 5. So let's go ahead and do that in Excel. So we have the data here for the problem. This shows the first column is the number of window lock sales, and the second column is the number of break-ins. The first thing we need to figure out is the dependent variable and the independent variable. According to the problem statement, you should be able to figure out that the number of break-ins is a factor, supposedly, a factor for the number of window lock sales. So that means that the window lock sales is the dependent variable y here, and the number of break-ins is x, the independent variable. All right, so what we next we want to do is, as I said before, it's a good practice to always plot our data to get a better understanding, deeper understanding of the data. So I'm gonna go to the insert tab here and the charts group here, and I'm gonna plot the scatter chart as you see here. So clearly there is an uprising trend. That means that as the number of break-ins increases, the number of the number of lock sales, window lock sales would increase. Also, not a perfect line, but you could see that yes, on average you could fit a line through your data. All right. So what we need to do is we need to figure out the components of a linear regression line, the slope B and the intercept A. You could use this formula in a painful computation way. I have broken already down this to two-part, the numerator and denominator here. You can compute that, but we're gonna do the efficient way, which is asking using the Excel's function slope to compute the B slope. So it has two parameters. The first one is the y variable, and the second one is the x variable. So y variable is the number of window locks sold, and the x variable is the number of break-ins. And there we go. We have 4.2753. And for the intercept, the function is intercept. And again, the first parameter is the y variable, or the number of window locks sold, and the x variable is the number of break-ins. So we have here we have computed also the intercept. So now we have the formula. We have the linear regression formula. We can use it to make a prediction for the problem. So the problem says that if the number of break-ins is 5, what would be the number of your estimation for the number of window lock sales? So according to the linear regression problem, that would be A intercept plus B multiplied by 5. So that's about 28.5. Our forecast estimation for the number of window lock sales, if the number of break-ins is 5, would be 28.5. We can also go ahead and compute the coefficient of correlation to judge the quality of or the expectation, the estimation of the quality of the regression model. So I'm going to use the correl function here. It doesn't matter, there's no x and y here, so you can just pick your data here, select your data, comma, the other variable, and we have 93% over R, and R square would be just the square of this R right here, which is about 86%. So this means that 86% of variation in the number of window locks sold in the market can be described by changes and variation in the number of breaks-in. So that means that it looks like there is a strong positive relationship between the number of break-ins and the number of window lock sales. There are a few important assumptions made for the linear regression model that is fundamental to understand when you want to apply it, so that you would not cross those the expectation or the scope of linear regression. And those assumptions are listed here. The first is the assumption that the variations around the regression line should be random. It's random. It's assumed to be random. That means there shouldn't be any types of trends or pattern within those data points. So if you see any pattern for your data points around the regression line, that's not a good indication. That's actually a violation of these assumptions. The second assumption is that the deviations around the average value, the line, the regression line, should be normally distributed. That means a large concentration of data should be around the line. That means that if you closer to this the linear regression line, there should be more concentration of data points compared to if you go further away to the left or to the right or to up and down on your regression line. That means if you vertically go away from the regression line in any direction, you should see less concentration of data points. The next assumption is that the predictions are made only within the range of observed values. This is very important. You could actually have a very good regression model with a high R-squared value, and then you could misuse that regression line easily and get actually an incorrect result. And this is very important to know when you apply the regression line and when you want to use it. Do not use the regression line for the, outside of the range that is accepted. So any prediction that are made should be within the range, accepted range, or the observed values. Few important notes and issues to consider when you want to develop a regression model for your data. As I stated before, this is a very good practice to always plot your data. No matter if you're developing a linear regression or whatever, plotting your data would give you a better understanding of your data, a deeper understanding. That would help you to analyze your data better and also probably pick a right method for or model for your data for prediction. And this is true also when you want to develop a linear regression model. So when you plot your data and you want to develop a linear regression model, you should be able to spot a line, a straight line. You should be able to imagine that you can fit a linear model or a straight line through your data. If the data that you have is time dependent, that means that you're dealing with a time series, a multivariate time series. That means you have more variable than just one. You have multiple independent variables. One of them is time. So you are dealing with a time series. then try to use time series analysis. And also use time as an independent variable, one of the independent variable. And you can use a multiple linear regression. That means that you have more than one independent variable. You have one independent variable, y is the same, but you have not just x. You have, for example, x1, x2, and multiple x's, different independent variables. And time could be one of them. Next point is to a small correlation. If you have a small if your linear regression model has a small correlation, that may indicate that there are other variables that you haven't considered that are important. So if you develop your linear regression model and then you find the correlation coefficient R and the value of it is small, that's an indication that the model is not as strong, or the relationship between the two variables that you have considered is small, is not as strong, or that's an indication that there could be some other types of variable or factor that you haven't considered in your model.